Welcome to the Physics Tips to Cambridge Students YouTube channel. Today we are going to be looking at the examples in uniform circular motion. Without much further ado, let's get started. So we're going to start off with the conical pendulum. Now in the conical pendulum, you find that the object will be describing a horizontal circle. Right, I think I need to show something there, like this one, right? So the tension is shown there as T is directed upwards, and the object's weight directed downwards shown in green, and then the acceleration towards the center of the circle. That is a conical pendulum, right? So looking at the diagram closely, you find that the acceleration is directed towards the center shown in green there, and then we have the tension directed upwards shown in black, and the weight going downwards is shown in red. So these are the forces acting on the mass, and the tension can be resolved horizontally and vertically as shown. T, so if this is our theta, then T cos theta will be in the vertical, and T sin theta will be in the horizontal. So the horizontal component of the tension gives rise to the centripetal force. Remember, we said in the second video that there can be one or two or three forces that give the centripetal force. So the resultant force is the centripetal force. So in this case, the resultant force is the component of the tension in the direction of the center of the circle, which will be T sine theta. So T cos theta is mg, and then T sine theta is mv squared over r, which is the formula for centripetal acceleration, or centripetal force, sorry. Now dividing the horizontal by the vertical equation, we have T sine theta, which is equal to mv squared over r, divided by T cos theta, which is equal to mg. The t's will cancel out. Sine theta over cos theta gives you tan theta, and then we have mv squared over r divided by mg. So the m's will cancel. You remain with v squared over rg, which is this one, v squared over rg, or gr. So the horizontal component of the tension provides the centripetal force in this case. Now before I look at the second one, this banking, you find that an aeroplane, when it's taking a turn, also has this circular motion, the horizontal circle. So I thought of just putting it as the horizontal circle there, which is similar to the conical pendulum. So there you are. The aeroplane's lift is going upwards at an angle, and then we do have the weight going downwards, and the angle between the lift and theta is theta. So the angle between lift and horizontal is theta. So if you resolve L vertical, it should be equal to the weight, because this aeroplane is turning but following a horizontal circle. It's following a horizontal circle. So L cos theta will be equal to mg in the same manner, and then L sine theta will be equal to the mv squared over r. Okay, so in this case, so this L cos theta being equal to mv squared over r, and then L sine theta being equal to that. So we are taking this horizontal angle instead of the theta that we used when we were looking at the conical pendulum. Right. So resolving vertically, you're going to get L sine theta, which is going to equal the mg, and then resolving horizontally, L cos theta is going to be equal to the centripetal force, which is your okay, I think that is that. Okay, let's see. So this is in the vertical, and then in the horizontal, we're going to get L cos theta being equal to mv squared over r. Okay. And then in the same manner, you're going to say sine theta over cos theta, going to give you that expression that we ended up with. Okay. Okay, so that's it. Okay, so that's the horizontal circle described by the plane as it is turning. Now let's move on to the next one, which is banking. So in banking, now we're looking at cars that are going in a circle or that are taking a bend or a curve. Now, to reduce the dependence on friction, the road surface is lifted up by an angle theta. This is called banking. So if we were to keep it as horizontal, you find that the dependence on friction is large. And if the friction is less, or there's little friction, suppose it has rained and the road is wet, you find so many cars skidding off the road. So to try and avoid that, you lift the road surface so that we reduce the dependency on friction, and that is called banking. So the angle theta is called the angle of bank. Okay, so let's see if I have something to show on banking. Right, so the road surface is lifted up, especially on curves, so that they can move. Okay, so I'll just show a bit. So that's the curve going through the curve like that. So that is raising that angle, which will be the banking. Okay, right, going back. So on a bank track, the normal reaction and the friction both have the component towards the center of the track. Right, so we can add the two, n sine theta. So theta, we're going to take this one as our theta. N sine theta will be towards the center of the circle. Then n cos theta will be equal to mg. Now at one particular speed, we're going to reduce this f to 0. So the component of f will be equal to 0 for a particular speed. So we end up with n sine theta is equal to mv squared over r, and n cos theta is equal to mg. And then we divide this first equation by the second to get tan theta is equal to v squared over rg. So the equation shows that for a given radius of band, the angle of banking is only correct for one speed. And then we have a car traveling over a circular bridge or humpback bridge. So the car is moving and then goes up. So we want to find that safe speed so that the car doesn't fly on top of the bridge like this. So in this case, the normal reaction force and the weight are the ones that are responsible for the centripetal force. So in order for the car to remain in contact with A, which means that W minus direction force should equal mv squared over r, because that's towards the center of the circle. The speed of the car is at a tangent to the circle as it goes up and down the bend or the humpback bridge. So at the top of the bridge, you say that we have got the reaction force, and then we've got the weight, and we say the weight minus reaction force is mv squared over r. The weight mg is constant, so as v increases, r must decrease. So when r is equal to 0, the wheels are just about to leave the ground. So the maximum speed at which this occurs, we equate the centripetal force to the weight. That is when there is no reaction force. So v will be equal to the square root of rg. Now in the case where you've got more reaction than the weight, right? That is, the car would fly. Okay, it would go it would fly on top of the bridge like that. So we want to keep R as minimum as possible so that the car can safely move through the humpback bridge. And then we have motion in a vertical circle, maximum and minimum tensions. So suppose here you have a bucket of water and you are welling it up like that in that direction. At the bottom, when the bucket is at the bottom, we have the weight going down. We have the normal direction or the tension of the string going up towards the center. So the resultant force between the tension and the weight gives you the centripetal force. So it will be T minus W being equal to mv squared over r. That is at the bottom right here. T, tension at the bottom, minus mg is equal to mv squared over r. Then at the top, the tension and the weight are both going in the same direction. So T plus the weight should give you mv squared over r. So T plus weight gives you mv squared over r. Then on the sides, the weight and the tension are perpendicular to each other. So only the tension is providing centripetal force. So tension will be equal to mv squared over r. Now, looking at this, if you make T the tension the subject at the bottom there, it gives you tension is equal to mv squared over r plus mg. And then if you have make the tension at the top, T is equal to mv squared minus mg. So which means the tension is greatest at the bottom. That is where the object is likely to snap off. That is, the string breaks and then the object continues moving at a tangent to the circle. So at the bottom, that's where you've got the greatest tension. At the top, that's where you've got the least tension. Okay, so if suppose there's water in the bucket and the bucket is moving like that, so the bucket and the contents, like the water, won't spill out as long as there is the certain speed, or we are above the certain speed. So the inertia of the water keeps it inside the bucket. But if you stop the bucket at the top there, all the water would spill out. Now, if remember we said that the tension, if the tension reduces to 0 right there, and the speed is low, then we should have all the water coming out of the bucket. But if there's sufficient speed and there's a little amount of tension in it, we have the bucket still continuing to move without spilling the water. Okay. Then we have looping the loop. This is normally found in roller coasters. So it is possible to loop the loop on a roller coaster ride without falling out. The forces acting on the ride are the weight and the reaction force, which is the contact force. So at the bottom, we have the contact force minus weight is equal to mv squared over r. At the top, the contact force plus the weight should equal mv squared over r. Right. So at the bottom, we said that's r minus mg is equal to mv squared over r. I said that. Then at the top, I said r plus mg is equal to mv squared over r. Then on the sides, the reaction, the contact force is equal to the mv squared over r. If it's at an angle like this, then we can resolve the direction force. Also, the component of it is the one that will be equal to the reaction force. So the centripetal force. Now, any speed slower, okay, let's see, as the speed of rotation decreases, mv squared decreases, and when rt becomes 0, then the man in the ride will just make the loop. Okay, when the normal reaction becomes 0, the man just makes the loop. Now, at any speed slower than this, that is mg will be greater than mv squared over r, the man falls out of his seat. So we talked about the water in the bucket, and that's that. And also the looping the loop. I think that must mark the end of this video. Please, if you have any questions, feel free to write in the comment section below, And don't forget to subscribe to the Physics Tips for Cambridge Students YouTube channel, as well as liking and pushing the notification bell. Signing out.